All right, we are continuing from where we stopped that day, the dot and cross diagram. And now let's look at some of the terms that is commonly used in chemical bonding, which includes the bond energy. A bond energy is used to measure the strength of the covalent bond. Another way that we can describe a covalent bond is to use its bond length. And bond length is measured from the center of one atom to the center of the other atom. So you can take a look at it as though like from nucleus to nucleus. So generally, the larger the bond length, it relates to a lower bond energy. Should be longer bond length. So when you have a longer bond length, it relates to a weaker bond and a lower bond energy. That's the general trend. Of course, fluorine shows that is a little bit different. For fluorine, the bond length is relatively short, but the bond energy is also quite weak. But that is because in fluorine, because of its size, there's significant amount of internuclear repulsion. Okay, but if we follow the general trend, we will see that when you have a larger or longer bond length, it translates to a lower bond energy. Now, same for orbitals. So when we have larger orbitals, and when you have larger orbitals overlapping, they will usually give us longer bond length. And therefore, weaker bond energy. Hence, right, if you look at the same grouped down the periodic table, and you will find that if we move from chlorine, maybe to bromine, and then maybe to iodine, you'll see that the orbitals are getting larger, and the effectiveness of the overlapping actually becomes poorer. And there'll be a longer bond length as a result, and a weaker bond energy. So this phenomenon is quite significant when it comes to double bond. So therefore, you will see that elements which are further down the group, they do not tend to form double bond. So let me give you an example. Example will be nitrogen. So you can see that nitrogen tends to form triple bond, whereas the next element below nitrogen, phosphorus, it can't form double bond. It can't form triple bond. But rather, phosphorus will form 3 single bonds instead to form a structure that has a structure that looks like this, which we call it P4. So it looks like this. Okay, so the same thing is seen for carbon also. So carbon tends to form double bond to form carbon dioxide. But when it comes to silicon dioxide, you'll find that silicon is unable to form double bond that well. So it will form single bonds with oxygen instead. And that is because when the orbitals are larger, their overlapping is actually less effective. And also because when their orbitals are larger, you have a longer bond length, and so the bond energy is actually weaker. Now, sometimes, right, they also use this term bond multiplicity to describe covalent bond. So although it sounds like a very difficult word, but these are things that you already learned before or heard before, such as single bond, double bond, triple bond. So these 3 terms are the common bond multiplicity that we use to describe the multiple bonds present in covalent bonds, right? So we can have a single bond. We can also have double bond and triple bond. Okay, so do not confuse bond multiplicity with bond order. So if we use the term bond multiplicity, it refers to single, double, triple. When we talk about bond order, of course, the bond order will be a numerical number. So it'll be 1, 2, 3. Okay, bond order does not have to be a whole number. So you can have bond order like 1.5, 1.333, etc. as when we come to the part of delocalization of electrons. Okay. Now, next, we can also have this term to describe a bond called bond polarity. Bond polarity means that in the bond, there's unequal distribution of shared electrons. So when there is a pair of electrons contributed for sharing between the two atoms, the sharing is not equal. Okay, but rather the more electronegative atom is pulling the electrons closer to itself. And as a result of that, it gives rise to some distribution of charges across the bond. And it gives the bond some form of ionic character in the covalent bond. So to describe the ionic character in the covalent bond, we will say that the bond is now polar. So often when you see a covalent bond, and sometimes you may see symbols like this, delta plus, delta minus on a covalent bond, it means that that bond is a polar covalent bond and the sharing of electrons between them is not equal, but the more electronegative atom is executing a greater attraction for the shared pair of electrons. So as a result of it, right, you can see some form of electrostatic forces of attraction between the delta plus and delta minus. So on top of covalent bonding present, there's also some form of attraction between the opposite charges. And therefore, generally, a polar bond is stronger than a non-polar bond. Okay, next we look at this special type of covalent bond, which we call coordination bond. So a coordination bond, we have seen it before when we were drawing the Lewis structure. So in a coordination bond, which is like a normal covalent bond, but a little bit different is that both the electrons of the shared pair actually comes from the same atom. So we have one atom donating a shared pair of electrons, while the other atom is not donating any electron. Okay, so both the sharing electrons are contributed by one atom only. And that atom that donates the electron, we will call it the donor atom. It actually consists of a lone pair of electrons for sharing. And another term that sometimes we use to describe this atom will be that we sometimes call it a Lewis base. So a Lewis base is a form of electron pair donor. So generally, what makes something suitable as a donor atom is that it must contain a lone pair of electron. Okay, now we will also have an acceptor atom. An acceptor atom usually consists of an empty orbital, and this empty orbital will then receive the pair of electrons from the donor. A term that we use to describe this acceptor atom will be Lewis acid, which means an electron pair acceptor. So what makes something suitable as a Lewis acid or as an acceptor atom? It must have an empty orbital, and it must have an empty orbital in its valence shell. So the donor atom must have a lone pair of electrons, while the acceptor atom must have an empty orbital. So in this way, a coordination bond can be formed between the two atoms. Now, in terms of property-wise, there is no difference in terms of property of a coordination bond and a normal covalent bond. The bond strength, bond length, and behavior will be the same. Sometimes in the Lewis structure, we will use the arrow to indicate that it's a coordination bond, but it's not necessary. Okay, it's not necessary, but if you prefer to indicate the coordination bond, then take note that the arrow will point from the donor to the acceptor atom. So if A is the donor and B is the acceptor, we will draw our arrow pointing from A to B. Now, often when we form a coordination bond, the purpose of forming is to allow the structure to achieve a stable octet configuration. So in this case, we have BF3, which is electron deficient. Why is it electron deficient? Because it has only 6 electrons after bonding. And the other molecule, ammonia, has a lone pair of electrons. So ammonia with the lone pair on the nitrogen will actually donate that pair of electron to BF3, and between them, they will form a coordination covalent bond, which makes BF3 more stable. So you can find that after bonding, if they will form this compound, NH3BF3, and if you look around boron after the coordination bond is formed, you will find that it has now a stable octet configuration of 8 electrons. Okay, now what other compounds form coordination bond? Any base that accepts a proton will form a coordination bond. This is our proton, H+. Hydrogen has only 1 electron as an atom. So when it loses an electron, it forms H+. So H+ has no electron in the structure. So with no electrons in the structure, it has an empty orbital. And any base that accepts H+, or any base that reacts with H+, will be forming a coordination bond with H+ to form the acid, the resulting product here. So ammonia, being a base accepting a H+, will form a coordination bond between the N and the H+ that it has accepted here. So after forming the coordination bond, you will find that all the 4 NH bonds are actually equivalent. You don't notice any difference in terms of its property. Okay? Another example of coordination bond forming is in AlCl3. So in AlCl3, because aluminium is actually electron deficient, you will find that there is a tendency for aluminium chloride, AlCl3, to bond with another molecule of AlCl3 to form a dimer. So what's the meaning of dimer? Dimer means 2 units joined together. Aluminium chloride is relatively quite unique. In the solid state, it behaves as an ionic compound, but when it is in the vapor phase, it tends to exist as molecules, but when it's at low temperature vapor phase, it tends to dimerize to form dimer. That means 2 units of aluminium chloride tend to join together to form Al2Cl6. And what's the evidence that we have to prove that dimerization happens? So the evidence that shows us that dimerization occurs in aluminium chloride in vapor phase is that we notice that the resulting MR of the aluminium chloride seems to be double of what is supposed to be. Okay, and to explain why the MR appears to be doubled, the only reason that we can propose is that it actually forms a dimer, which means that 2 units of AlCl3 actually join together to form Al2Cl6, and therefore the measured MR appears to be double of the AlCl3. And again, the driving force behind dimerization and coordination bond formation in this case is also trying to achieve a stable electronic configuration. So you can see this is AlCl3, 1 unit, and this is the other unit of AlCl3. Looking at aluminium, before dimerization happens, it has only 6 electrons. So a lone pair on the chlorine atom of another molecule will therefore form a coordination bond with one of the molecule, and a lone pair on the chlorine atom of another molecule will form a coordination bond with the aluminium of another molecule. So it looks like this. 2 dative bonds being formed, holding the two units together. So two of the aluminum chlorine bonds are coordination bonds, which hold the two AlCl3 units together. And the donor in this case, or the Lewis base in this case, will be the chlorine atom. And the acceptor in this case is aluminum, which is acting as a Lewis acid. All right, so let's move on to the next term that we're going to look at. So we are moving away from the VSEPR first to look at the different terms. Okay, moving on to page 24. So in this chapter, we often use the idea of electronegativity, which is the attraction that an atom has for the shared pair of electrons in a covalent bond. So if we apply this definition strictly, you will find that this term should only be applied in a covalent bond. Okay, because that's when you have a shared pair of electrons. So as shown earlier to you, that electronegativity values can be found in the data booklet. And generally, if you don't have a data booklet, the electronegative elements, the most electronegative elements are found on the top right-hand corner of the periodic table. It's because you can see that as we move across the period, there's increasing number of protons, which give us increasing nuclear charges, and so increasing attraction for our electrons. So as a result, we have stronger electrostatic attraction between the nucleus and the bonding pair of electrons, and therefore electronegativity increases across the period. Moving down the group from fluorine, chlorine, bromine, iodine, you will find that very obvious, there is actually an increase in number of energy levels. So with the increase in energy levels, it actually results in an increased distance between the nucleus and the bonding electrons, or your valence electrons. And that increased distance actually will result in a decrease in attraction for the shared pair of electrons. And hence, down the group, electronegativity or the attraction for the shared pair of electron decreases. So generally, when we have two atoms, most of the time we will work out what's the electronegativity difference between the two atoms. If the difference is small or less than 0.4 or 0.4 to maybe around 0 to 0.4, okay? If you have such a case whereby the electronegativity difference is either 0 or less than 0.4 or 0.4, we can classify this as a non-polar covalent bond. So in a non-polar covalent bond, we are assuming that the pair of electrons is shared equally between the two atoms. Again, if we have very extreme electronegativity difference, which is, for example, like more than 1.8, then we will classify this bond as an ionic bond, where they are no longer sharing electrons, but the electrons are going to be transferred from one atom to the other atom to form cations and anions. So what about those values that's between 0.4 and maybe 1.8? So for those values between 0.4 and 1.8, we would usually classify them as a polar covalent bond. So when we have a polar covalent bond, it means that there's no, the shared pair of electrons is not being shared equally between the two atoms, but rather the more electronegative atom will exert a stronger pull for the shared pair of electrons, and this results in some form of partial charges being developed on the atom. So you can see from this picture here, a pure covalent bond is where there is equal sharing, when the electronegativity difference is 0 or relatively very small, like 0.4. And we can have a covalent bond with some ionic character, which we call this covalent bond a polar covalent bond. in this case, there is unequal sharing of electrons because the more electronegative atom is pulling that shared pair of electrons more, and this gives rise to partial charges developing across the bond. And these partial charges, we will indicate it by using delta minus, delta plus. So the more electronegative atom will carry the delta minus charge, while the less electronegative atom in the covalent bond will carry the delta positive charge. But they are still sharing the electron. So it's not like in the case like an ionic bond where you have cations and anions. All right, so this is the table that you can refer to. But again, there's some form of limitation in this numbering system. So of course, the best way is to use the triangular bonding diagram. So when we look at a non-polar bond, for example, in hydrogen, H2Cl2, definitely the bonding electrons will be shared equally because there will be no electronegativity difference between them. Right? So in this case, there will not be any partial charges being developed. But if we look at a covalent bond, which is polar, like HCl, Cl being more electronegative than hydrogen, the electrons will not be shared equally now. So the electrons are shared unequally because of differences in electronegativity values. And therefore, there's a form of distortion of the electron density. And this distortion of the electron density is called polarization. And we say that this covalent bond is polar. So a polar bond usually will carry some partial positive, partial negative charges on the atoms due to the uneven distribution of the electrons. So the more electronegative atom will therefore carry a higher electron density. So it will have a partial negative charge on it as indicated by delta minus, and the less electronegative atom will have a partial positive charge on it. Now, whenever there are charges and they are separated over a distance, it will create a dipole. So when there's a charge separation across a distance, it creates a dipole. And so a polar bond will therefore have a small dipole moment. And a dipole moment is usually a vector quantity. So there are two properties that's associated with the vector. There is the magnitude as well as the direction. So how do we indicate a dipole on the molecule or on the bond? So for example, if I have HCl, we can indicate or draw the dipole on the molecule by using a symbol like this, an arrow with a line. So when we draw this dipole, an arrow with the line, so make sure that the arrowhead is pointing towards the more electronegative atom. Now, what is the impact of having a dipole and not a dipole on the molecule? So you'll find that for molecules with no dipole, if you place that molecule in an electric field, the molecules are not affected by the electric field at all. So before you turn on the electric field, the molecules are in random arrangement. After you turn on the electric field, the molecules are still in random arrangement. So this is the case for non-polar molecule. Whereas if you have a polar molecule, which has a dipole, before you turn on any electric field, the molecules are in random arrangement. But after you turn on the electric field, you will find that the molecules with dipole, they're actually lined up in the same direction with the opposite charges facing the magnetic field. With the opposite charges facing the electric field. Okay, so we will have the minus end facing the positive end of the electric field. So there are three types of dipole generally. We have permanent dipole, we have temporary dipole, we can also have induced dipole. So what's the difference between them? A permanent dipole exists in every polar bond, or polar molecule. So when you have a simple molecule, like for example HCl, you will see a permanent dipole present in the HCl molecule. And this permanent dipole arises because of difference in electronegativity of the atoms. So in this case, because of the electronegativity difference of H and Cl, there will be a permanent dipole existing in the molecule. Okay, that's what we have been discussing. It will always be there, this dipole. Now, a temporary dipole, or what we call as an instantaneous induced dipole, it could be present in nonpolar molecules. So in nonpolar molecules, for example, like O2, H2, N2, there are no permanent dipoles present because there's no electronegativity difference, and the electron clouds distributions are equal. Okay, but however, because they are in the environment, there could be sudden fluctuation of the electron cloud. And when that happens, due to the sudden fluctuation of electron cloud in the environment, you may have that for a moment, there could be a positive and negative charge arising on the molecule. And this gives us a temporary dipole, or we can call that an instantaneous dipole that occurred for a very short time. So for example, we can have a nonpolar molecule like hydrogen, H2, and because of temporary fluctuation of its electron cloud due to the environment, for that split second or that moment, you may see that the electron cloud becomes unevenly distributed. And once that happens, there will be a temporary or instantaneous dipole forming. Same for your noble gases. Your noble gases doesn't form any bonds with other atoms. So basically it's on its own. So the electron cloud, if it's subjected to some temporary fluctuations, it may result in a slight distortion. And when that happens, an instantaneous dipole may appear on the molecule for a short time. An induced dipole is a little bit different. So when you have a molecule having a dipole comes into contact with another molecule that has no dipole, the presence of the molecule with a dipole may induce a temporary dipole, or it may induce a dipole on the molecule that is nonpolar. So over here, we have our HCl molecule, which has a permanent dipole, and it has a permanent delta plus, delta minus N. And if we bring it near a helium atom, what will happen is that the delta minus N will cause the electron cloud of the helium to be repelled away. And as a result, it will distort the electron cloud of the helium because it's being near to it. And that causes a slight or a momentary charge buildup, distribution of charges on the atom, because the electron clouds is now no longer symmetrical. And this gives rise to an induced dipole. So the induced dipole will stay there as long as the HCl is still around. By the moment, if you remove this HCl, it will revert back to a symmetrical electron cloud, and this induced dipole will be gone. So in a way, it's not permanently there, unlike the permanent dipole moment. All right, so that is about the polarity of bond. So now we look at the polarity of a molecule. So when you have molecules with polar bonds, they can be polar and they can also be non-polar. So we can have some molecules which has polar bonds ended up being polar. We can also have some molecules with polar bonds but ended up being non-polar. And how does it happen? So we can have polar bonds And the presence of polar bonds can possibly give us a polar molecule, or it can give us a non-polar molecule. So what's the difference in each case? Okay, so you'll find that it has to do with whether the dipole moments can cancel out in each case. So remember, dipoles behaves like it's a vector quantity. So dipoles has a direction as well as a magnitude. So if we apply vector addition to the molecule and sum up all the dipole moments, and after doing so, if there is a net dipole moment for the molecule, then the molecule is polar. But if we sum up the dipole moments and we find that the dipole magnitude and the dipole direction allows the dipole moments to cancel each other nicely, giving us zero net dipole moment, then the molecule will be non-polar. All right, so let's look at some example, okay? So over here, HF. So the dipole moment is pointing towards F. And there's only one dipole moment, so there's no way it can be cancelled out. So therefore, it will always be there. So there is a net dipole moment in the molecule, so HF is polar. If we look at HCl, okay, if we look at HCl, we can take as the CH bond as non-polar, because if you look at the data booklet, the electronegativity between C and H is quite small. So there's only a dipole moment this way between the C and Cl. So you'll find that with one dipole moment in the molecule, there's no way it can be cancelled out. So when I sum up all the dipoles present, there is a net dipole moment in the molecule. And so the molecule is a polar molecule. Okay, now same for H2O. If we draw the dipole moments of the bond, OH bond here, and OH bond here, with the arrowhead pointing towards O, which is more electronegative, you'll see that when you sum up this vector and this vector, it actually gives you an overall vector in this direction. So there is an overall vector present in the molecule, and therefore it is a polar molecule. Okay, next, let's look at some molecules where the dipole moments can cancel out nicely. So in this case, like CO2, each bond is polar. Between the C and O, we have a polar bond with the arrow pointing towards O, which is more electronegative. And we have a polar bond pointing towards O with a dipole moment pointing towards O. Now, this is a CO and this is a CO. So the magnitude will be the same. So you can see that based on the direction and based on the magnitude, in this case, when we sum up the dipoles, they cancel out nicely. So because the dipoles cancel out nicely, we have a net zero dipole moment, and therefore this molecule is non-polar even though the bonds are polar. Okay, I repeat. So this molecule is non-polar even though the bonds are polar. Same for CCl. So in CCl case, if we draw in the dipole moments for all the bonds, you will find that since the bonds are all CCl, so the magnitude will be the same for the vectors. But when we sum them up, you will find that they cancel each other nicely. So again, CCl bond is polar, but when we sum up all the dipoles in the molecule, you will get a net dipole that's equals to 0. And so this molecule is non-polar. All right. So to summarize, for a covalent molecule to be polar, we must definitely have a polar bond so that we have a dipole moment to start off with. And the dipole moments must not cancel out, such that at the end of the day, when we sum up all the dipole moments, there will be a net dipole in the molecule. And so what causes the dipole to cancel out, etc.? It depends on the direction, it depends on the magnitude, it depends on the shape of the molecule. So that's why you must draw your structure, Lewis structure, correctly, so that when you apply your VSEPR, you get the correct shape. Then you can deduce whether the vectors or the dipole moments cancel out each other. Okay, I think we will stop here first because there's quite a lot for you to follow up already.